Okay, so just to remind everyone here that we want to give Dr. He a chance to explain what he's done in terms of the science in particular, but also other aspects of what he's done. So please, can you allow him to speak without interruptions? As I said, I have the right to just cancel the session if there's too much noise and interruption. And I just wanted to state a couple of other things. So first of all, that we didn't know the story that was going to break over the last couple of days when he accepted the invitation to come and speak to us. So we didn't know this story beforehand. In fact, he had sent me the slides he was going to show in this session, and it did not include any of the work that he's now going to talk about. It was sort of preclinical data, but nothing involving human embryos that were implanted. And I should also state that we're in a venue. We have very generous hosts, Hong Kong University of Hong Kong. And our hosts have a strong tradition of allowing free speech. And so we are complying with that tradition of free speech. So anyway, I would like to, if you can hear me, ask Jiankui to come to the stage and present his I don't know where he is, so okay. All right.
Okay, thank you. First, I must apologize that this result leaked unexpectedly, taken away from the community of the full data being presented immediately in a scientific venue. And through a peer review process engaged before this conference. So this study Thank you. Okay, so this study has been submitted to a scientific journal for review. I also thank the Associate Press, who we engaged months before the child's birth, of a commitment to the accurate reporting the study's outcome from many points of view. I also thank my university, although they are unaware of the study's conduct. So, Winnie Herbert, I should also thank you for your statements now and your wisdom that shared with me, as well as the community for discussing this data and providing this forum. I'll give an overview of our data focused on human and monkeys. Despite wonderful progress in HIV therapy and access to this therapy, new infections remain 3 times higher than the AIDS 2020 target. So HIV remains a top 10 cause of death in several countries, in particular developing countries. For uninfected children born by an HIV-positive mother, who make up a large percentage of births in area of Southern Africa. The risk of being infected by HIV in the first few months of life is many, many times higher than other babies. This is a serious unmet need, as an infection's severity is often made even worse by discrimination. So a copy of a natural protective allele against HIV infection is carried by as much as about 10% of the population in several European countries. This allele led to the first functional cure of HIV and decades of clinical trials, making this natural small deletion in CCR5 gene one of most studied variations, and the CCR5 gene are one of the most understood genes. We first explored the impact of CCR5 gene knockout in mice to investigate multi-generation effect. Editing was efficient as expected. We established a third generation CCR5 lung mice, which we confirmed by Western blot and flow cytometry. Tissue pathology was normal in heart, liver, lung, and stomach. So, two common behavior assessment showed no difference. We then assess whether this should get RNA against the human CCR5 gene could be designed. So we assessed 7. I highlighted one that occurred at exactly the start of delta 32 mutation. It has an MAT specificity score above threshold, predictive of having no off-target activity. A few previous publications has assessed the same or similar GATA RNA in multi-cell type, including non-viable embryos. SG4 induced the most efficient editing activity in a cell line and 3PN human embryos. Since this target site is conserved in the monkey genome, we could use the monkey as an animal model to assess the SGRN further. We found injecting the Cas9 closer to fertilization promoted the most efficient editing efficiency. Consistent with the Cas9 require time to find the target loss and its degradation over time. The rate of fertile eggs forming blood cells was not affected by exposure to Cas9, which we observed across experiments. So sequencing of the blood cells quadrant confirmed earlier Cas9 injection also reduced the mosaicism. To look more closely on the mosaicism, we also sequenced every individual cell in several embryos. Editing appeared to occur at the 1, 2, 3 cell stage. On the assumption that Cas9 degrades quickly and requires time to find the right target, we explored a strategy to reduce the mosaicism by delivering a second injection of Cas9 to an embryo at the 2-cell stage. The development of eggs to the blood cells was not impaired. We expanded sample size, which confirmed this previous observation. We still observed the variation across parents and the cycles. We then looked to see if this protocol could translate to human embryos. We found, as others have reported, the Cas9 protein was the most efficient delivery format. Lowering the dose compared to the monkey embryo also improved the efficacy. Upon the advice I received after presenting early results at the February 2017, the UC Berkeley genome editing workshop, we edited non-viable embryos and established 2 embryonic stem cell names. So both are bioanic lockout and the karyotypes are normal. Embryonic stem cell marker expression was normal by staining and the flow cytometry. This embryonic stem cell also found all 3 germ layers during the 14-day EV experiment, which is a marker of safety. Another serious safety concern is off-target. Embryo editing target a single or few cell stage of life. Any off-target would pose very serious consequence and extend potential through the whole body. In adult gene therapy, off-target are expected, but a less healthy problem. We assess the off-target initially by single-cell whole genome sequencing of embryo prior to the implantation. We use the isothermal MDA amplification method to minimize the false positive rate and for unbiased coverage. The Both lab use the same approach. We take a step further by sequencing the parent genome to detect off-target risk sites that exist only for each parent and a particular embryo, but not in the reference genome. We create a pool of off-target risk sites by first collecting any sites mentioned in previous publication. We added the genome sites for the unbiased assessment of a potential cleavage site. And in silico prediction, such as the MIT CRISPR design, both the original and the 2018 updated version. Finally, we import the parent genome, which allow facing to improve sensitivity and detect the novel risk sites unique to each embryo, which may emerge from inherited indel or SNPs. So all these loci form a personalized pool on the order of 10,000 spots per embryo. We use whole genome sequencing to assess for the spots and validate any findings by single sequencing. I will review genome sequencing data with the data on the null and the nana as focus and end. Of the potential cleavage sites identified by the genome-wide unbiased digenome assay, none was observed in the whole genome sequencing data. And no activity was observed at the risk sites identified by the 2018 version of MIT technology, MIT CRISPR design software and the original version. We explore off-target in the HESC7 generated from edited embryo. Although we didn't have access to embryo with the parental donor's genome, we identified one potential off-target. This off-target is in an intergenic region, although we cannot confirm whether this is an inherited or is due to editing. So here you can see the editing efficiency across 19 viable embryos from volunteers. So we performed PGD, whole genome sequencing across the embryo, and didn't identify the off-target sites. So in one embryo, we identified 6 KB deletion at the on-target sites. It did not affect any gene but CCR5. The CCR5 gene's distance from other genes protect against the risk of large deletion. We detect the large deletion by assessing for the chimerical reads and the visual confirmation. Now I will focus on the Lulu and Lala's genomic data. We sequenced the genome of both parents to confirm the target site conservation and to support off-target detection. The mother was HIV active, the father positive, with undetectable viral load. So the ICSI and the sperm washing was used to prevent transmission. At day 5, so we have few cells were sampled from blood site for PGD. We follow on these results during the pregnancy by cell-free DNA after the mother declined on amniocentesis. So Lulu and Lala were born normal and healthy, with outcome score 8 and 9. After birth, we sequenced several different tissues. So in this Mark and Grace's first IVF cycle, pre-implantation genetic diagnosis found 2 blood sites were edited. One was a bionic frame shift lockup, which showed shortened the CSAF protein, similar to the natural protective variation. Another has an in-free deletion in one allele. The deletion expects to destabilize local protein structure in the nearby HIV binding sites. The parents were informed of implementation of this in related to HIV infection and reminded them the option to leave the trial without implementation or to choose the wild-type embryos. The couple elected to implant this embryo to start a 2-embryo pregnancy. In addition to the single data, we also reported to the volunteer whole genome sequencing data. The reads cover more than 80% of the genome. The whole genome sequencing identified one off-target in the MEG-based intergenic region far from other genes, with no coding RNA and transcription factor binding sites. The volunteers were informed of the risk posed by the existence of one potential off-target, and they decided to implant. After the mother declared amniocentesis, serial cell-free DNA of blood test didn't observe the intergenic off-target from PGD. So another cell-free DNA test found no larval cancer gene mutation. After birth, the deep sequencing of the cord blood, which is primarily the baby's blood, confirmed editing pattern observed during PGD and cell-free DNA. Sangal sequencing also confirmed this observation. After birth, both MySeq deep sequencing and Sangal sequencing did not detect intergenic off-target observed during the PGD. This suggests it was an artifact of a single-cell amplification or a mosaic off-target that happened to occur in the few trophoblast cells sampled for PGD. For whole genome sequencing, we did a 100x cord blood and 30x on the placental. No off-target were observed genome-wide. Neither were large deletion. We will continue to assess the effect of editing in the twins, including testing a blood sample for susceptibility to HIV infection at the P3 biosafety lab. We also further investigate the off-target effects and the mosaicisms across multiple tissues. And plan to monitor the twins healthy for the next 18 years with the hope that they will consent as adults for continued monitoring and support. Thank you. Okay, so.
Okay, so what we're going to do is have a little panel discussion, just the three of us, to make sure that the details of the science are well understood before we open it up to some general questions. Okay. So Matt is up here to help me with this. So Matt, do you want to start or shall I start? Okay. You chose to work with CCR5 because you felt that this was a valid first gene to target with this approach. But do we really know enough about CCR5 and its function? Because, as you said, that there are naturally occurring mutations. There are many, probably millions of people who naturally have mutations in the CCR5 gene. They're mostly northern European, or that's thought to be the origin of it. It's very infrequent, at least the delta 32 mutation is very infrequent in China, for example. So that could be that could reflect either that it never spread here from Northern Europe, or that it's selected against in China. So it's known that having mutation in CCR5 protects against HIV infection, but does it predispose to other complications. So West Nile virus, we know there's some evidence to suggest that increased that. And then just a long question, I'm sorry, but well, answer that one first. What about other things? There's also a suggestion that maybe influenza, so patients with CCR5 mutations may be more susceptible to severe effects of influenza, which would be bad in this part of the world.
Okay, so we choose the CCR5. It's for multiple reasons. So first, it's HIV. It's a lethal disease in several developing countries, and also this HIV exposed but uninfected children became a new global challenge. And their study in Zambia, also study in China, show that those HEU children may get affected from 6 months to 18 months in this 1 year period, with a possibility of 0.5 to 2.5%. So that's a significant number compared to the kids in general. And so for this gene, we have studied for decades, and there's multiple clinical trials on that. And also for the Western layer and other potential side effect of this, so during the informed consent, it was written down to inform them will be Western layer virus, not infections. And also in our 18 years old, even longer monitoring program, there's the Western layer virus detection regularly.
And do you want to follow up on that, or shall I? One follow up a bit more on that. So, so there's this, the CCR5 obviously must have a function in the immune system where it normally operates, which is nothing to do with HIV. The immune system, we know, has effects throughout the body, and that includes the brain. Right? It's known to affect aspects of functioning of the hypothalamus, pituitary, the other aspects of brain function. You cited your own work on looking at some evidence to suggest that there was no effect on behavior or cognition, but there has been another paper published a couple of years ago suggesting that actually mice with mutations in CCR5 had enhanced cognitive ability. So that poses an issue, because have you inadvertently caused an enhancement at the same time as dealing with this? So do you think we really know enough about CCR5 and its role in the immune system to choose that as a first gene?
Okay, so the first is I against using the genome editing for the enhancement. Second, so the study you mentioned, I saw the paper, and I believe we need more independent lab verification. And also for the CCR5, we start this. Another reason is we should start with some simple, well understood single gene as became a conservative first model, so that maybe in the future you move on to multiple gene, more complicated genotypes.
Okay, well, Matt.
So thank you for your clear presentation. I think there's going to be some questions about some of the numbers in the process. So for example, how many couples have you consented? How many eggs have you obtained from each mother? How many embryos have you attempted to modify? How many then had the correct modification? And then how many were attempted to be implanted? And then how many actually gave way to birth? So what's the pipeline that you have done as part of this project?
So there are in total 8 couples enrolled for this study, and 1 dropped out. And for the remaining 7 couples,
Excuse me, and they were all similar in father was HIV positive, mother was HIV negative?
Yes, the enrollment criteria requires the father to be HIV positive and the mother to be HIV negative, and plus some other age requirement and others. So, so for all the couples, they after informed consent for multiple rounds, informed consent with scientists and also with the team members, and then under the normal IVF procedure. So collect eggs, and then we inject casein protein and get RNA.
And sorry, how many eggs total between the 7 couples?
So in total, we have about 31 processes. But that number is it's 30 embryo process that are deep. Yeah.
So 31 were injected.
It's more. I mean, when it's 30, it's developed to process stage, and with that, about 70% of the embryo were edited.
70% had biallelic editing, or 70% had monoallelic? And what was the percent mosaicism in those 30 embryos when you, well, that's right, you wouldn't know because you only took 1 cell.
Yeah.
So, and then, okay, so why did you decide on these 2 rather than the other 24?
This couple happened to be first to be pregnant.
Have you subsequently implanted the remaining in the 6 other couples?
So the clinical trial was paused due to the current situation.
I have one other thought. I'm from the United States, so I'm not completely familiar with how the review process. So how did you go through, who did you discuss this trial with in terms of your supervisors, mentors, other people, in terms of getting feedback on the trial design, the consent process? Tell me sort of the scope of the team that was involved in designing this clinical trial.
Okay. So when I start this, even from the preclinical study, I first talked to a couple scientists and doctor to find out CCR5 is the one to recommend. And then once I have some early data on the preclinical, I presented in the Cold Spring Harbor Lab meeting in New York in 2017, and also in the UC Berkeley Genome Editing Conference. So some of the audience also in that conference too. So I get feedbacks, positive feedbacks, and also criticisms, and also some constructive advices. And I continue to talk to not just scientists, but also the top ethicists in the United States at Stanford, like Winnie Herbert, as mentioned, multiple times talk. And also I show my preclinical data to many scientists visiting. When I started the clinical trial for the informed consent, it's we take the NIH guideline as a reference and drafted the informed consent, and later was reviewed by a U.S. professor. And when it's pregnant, this informed consent was reviewed again. So at a subsequent supplementary material for the informed consent to add the long-term follow-on plan. And also.
Let me go to that. How many people read the informed consent before you showed it to the family? How many people reviewed the informed consent and felt like it was appropriate?
So outside of my team, there are about 4 people. And when this couple was informed consent, there's observer from United States professor and also a Chinese professor in the Chinese Academy of Science, and it's audio recorded.
Yeah. So on the informed consent issue, was that gained by an independent person talking to the patients, or were you or your team involved in that process directly?
That's including the first round is team member went to talk to the volunteer first for 2 hours. And then after about 1 month, the volunteers came to Shenzhen. And I personally, together with another professor, give up 1 hour and 10 minutes informed consent.
But you were directly involved?
Directly involved. Because after 1 month, they actually bring out the papers, say off-target, CRISPR things, already information there.
And one more question, maybe even upstream. How did you recruit these couples into your study? Was it done by personal connections? Did your institute put out a release? So how was the recruitment done of these particular couples?
It's by HIV and AIDS volunteer group.